Okay. Hello, everyone. This is Jose Campos, and together with my colleagues Pablo Recaros and Rodrigo Sandoval, we will present our work entitled Cascade Control Applied to a Single Component, Single Stage Vaporizer, Modeling and Simulation Approach. This work focuses on the dynamic modeling and advanced control of an LPG vaporization system using both a single loop and cascade control strategies. First of all, I want to say that this work is already published and is in an open access way. The journal is the Journal of Electronic and Electrical Engineering by Universal Weiser Publishers. So if you wanted to know more detail, please access to this document. Now, the presentation is structured as follows. We will begin with an introduction, then we will talk about the process description. After that, we will move on to the process modeling, then we will move on to the control system design, then we will show you some simulation results to end with some conclusions. So we will begin with the introduction where the motivation and research gap are present. LPG vaporization is a critical operation in many industrial plants, as maybe you know. However, it is also one of the most difficult thermal processes to operate safely due to strong nonlinearities, coupled thermodynamic dynamics, and phase change phenomena. So, safe operation requires well-trained and structured control systems. From the literature review, we identified a gap. For instance, a very few words combine rigorous nonlinear modeling, anticipated linearization, and structural control system design. Now, the objective of this work is therefore to derive nonlinear dynamic models, to linearize them into the space representation, to finally design robust control system for a level and temperature regulation. The contribution includes fast disturbance rejection, minimal overshoot, and negligible steady state error. Now we move to the process description. The system consisted in a pressurized cylindric vaporizer tank. Main elements are LPG controlled by valve 1, as you can see in the process diagram in figure 1, vapor steam heating coil controlled by valve number 2, vapor outlets with condensate trap. The main control variable are liquid level, which is designed as HT, pressure, which is labeled as PNT, and condensate temperature, which is labeled as TS and T. This configuration, of course, introduces strong coupling between pressure, temperature, and liquid dynamics. Two control strategies were evaluated: a single loop feedback control for liquid level, cascade control for pressure and temperature. The performance was evaluated using figure of merit like, for instance, overshoot less than 5%, steady state error less than 1%, and those criteria ensure industrial applicability in order to have some tunings with real cases. Now we proceed to the process modeling. The modeling state begins with mass balance of the liquid phase, energy balance of the system, vapor phase pressure dynamics. Now, the model capture, as you can see here, of course, right? Nonlinear thermodynamic behavior, coupled hydraulic thermal interaction, and valve depends inflow and steam heat transfer. Now, the nonlinear model is derived from conservation of mass, conservation of energy, and inner gas relationships for vapor phase. But also you can see that the system results in a set of nonlinear differential equations describing liquid height dynamics, vapor pressure evolution, and thermal energy exchange. Now, for control design, the nonlinear model was linearized around the operation point as you can see there, right, in this slide, expressed in a state space form. So we think that with this approach, it is possible to get some classic control technique, and we can apply it in this linear model, preserving at the same time physical interpolation. Now we will discuss a control system design. Two control structures were implemented. In the first time, single loop control, where PID controller was applied for a liquid level. Then a cascade control, where the outer loop is related to the condensed temperature TS, and the inner loop relate to the pressure PNT. But at the same time, manipulated variables are valve 1 position, which is labeled as K1 on T, and valve 2 position, which is labeled as a K2 on T. Cascade control improved disturbance rejection and robustness, as the theory states. Now, design objectives include minimize overshoot, ensure fast convergence, achieve negligible steady-state error, improve disturbance rejection, and of course, the controllers were trying to satisfy industrial figure of merit, which were stated in the slide before that. Now we move to simulation result. For level control, for instance, the system shows stable behavior, as you can see in this figure number 3, minimal overshoot, zero steady-state error, and the step change were applied at 200 seconds and 400 seconds. The controller maintains stability under transient conditions. Now, with the cascade control, the pressure regulation is significantly improved. The pressure control becomes more robust, and disturbances in LPG and steam flow are effectively compensated. The manipulated flow, in this case, are LPG inflow and steam flow. And those flows show more dynamic behavior without oscillation. This indicates good controller timing and actuator stability. Now, valve position remains within realistic operation bounds, if you can see in this slide. No acceleration or instability was observed for a long time. And this confirmed in somehow a practical feasibility. The performance result show an overshoot less than 5% and a steady state error less than 1%, and a strong robustness under disturbances. So cascade control, in our point of view, show a clear outperformance to single loop control way. Finally, we conclude, basically this work, develop nonlinear and linearized model, design a dual control strategy, demonstrate robust and precise dynamic performance. Practical implication include, for instance, safer vaporizer operation, improve reliability, and enhance disturbance rejection. Future development can include, for instance, refinement on the startup stage, reduction of initialization overshoot, and extension to multi-component vaporization system. Thank you. That's all.